the 5 core developers and go pretty much far with it.
Okay, now it's 10 o'clock. Do I need the microphone or is it okay without it? Okay. So welcome, thanks for coming. One of my first impressions of this lecture was that someone, he asked me in the elevator, oh hi, will you give another funny talk about APL? That's, I think, as strange as it can get on a Perl conference to be asked about APL. But he was right in some way, because 5 programming language implemented in Perl resembles APL to a certain degree. Why would anyone implement an array-based stack language in Perl? Of course, you have to like array-based languages like APL, and especially I am really missing Rex APL. This was an APL interpreter by Digital Equipment Computer Corporation, and they stopped support about 10 or 20 years ago, and I'm really missing Rex APL. So Thomas and I had the idea, why not write our own stack-based array language using our main programming language, Perl. And the result of this is 5, called 5 of course because it's a blend between APL and Forth. Why would one blend 2 strange languages like APL and Forth? It's quite simple. Both have strengths and weaknesses, and the combination of both combines most of the strengths and levels of the weaknesses. APL is incredibly powerful. It's really incredible what you can do with a single line of strange APL characters. And it's also incredible what you can do with a Forth interpreter. It's so highly interactive. You can develop your Forth words, aka subroutines, on the fly, test them, and incorporate them in larger programs. You can extend the language by itself. And this was the idea, okay, we will take APL and Forth and create a new programming language called 5, implemented in Perl. By the way, yesterday we had a small hackathon, about 2 hours, using NYT-prof. We were able to speed up the interpreter by a factor of 3 in 2 hours, thanks to Tim Bunn's NYT-prof. Of course, I re-implemented Larry Ward's examples he gave on his keynote on the first day. For example, the perfect numbers and the 5 program to calculate all perfect numbers between 1 and 500 ran 6 seconds, nearly 6 seconds before our speed up, and now it runs 1.2 seconds. Okay, APL has its weaknesses. Some of you may remember this slide. This is a real APL routine. That's not a joke. That's a fast Fourier transformation in APL. That's as horrible as it can get. I have no idea how this works. I really tried to understand it, and I gave up after some days. No way to figure out what this does. So the major difficulty in APL is this character set. You need a graphic terminal. You cannot do this with a simple telnet or SSH connection. It's really horrible. And furthermore, APL, does any one of you know of more than one free APL distribution? No. The only free APL I know about is A+ from Morgan Stanley. All other APLs are extremely expensive or only intended for hobbyists to use. So what we did is we wrote our own interpreter language, and as I already mentioned, we blended APL and Forth. So our only data structure is a stack. But in contrast to simple Forth, where the stack can only hold integers or sometimes floats, depending on the dialect you're using, 5 is able to hold arbitrary structures on the stack. You can put a 10-dimensional array as a single element on the stack and perform some operations on these arrays. So 5 is as interactive as Forth is. It looks like Forth. You can do nearly everything you can do in Forth if you leave out the array part, and you can do nearly everything you can do in APL. Although we are still missing some routines which APL supplies, like transpose on various axes. This is our next hackathon project. Okay, let's have a look at a real world example of 5. Calculate the Gauss sum from 1 to 100, or 100, the factorial of 100. Doing this in 5 is fairly simple, and you see no loops at all. That's the main strength of array languages, as the examples of Larry Wall 2 days ago showed in Perl 6. To compute the sum of all natural numbers between 1 and 100, you would just define a new word. Colon Gauss starts the definition of a new word, Gauss, and this word just consists of iota 1 plus quote plus reduce. Okay, what does this do? Don't forget, you have to think like Yoda, it's a stack-based language. So Gauss expects a value on the stack and applies the iota operator. It's named iota because its equivalent in APL is named iota2. Iota creates a vector with unity stride starting at 0. In this case, APL would start at 1 and running for a length of 100 in this case. So we have a vector 0, 1, 2, 3, and so on till 99. 1 pushes a 1 on top of this vector of the stack, plus adds this 1 to every single element of the vector we created with iota. Quote plus pushes the operator plus on the stack. It does not execute the operator. And the reduce operator is the same as reduce is in APL. It applies this operator between each successive element of the vector. So what we get is 1 plus 2 plus 3 plus and so on plus 99 plus 100, and this will just yield 5050 as a result. The factorial function works exactly the same way, with the difference that the operator is, of course, a multiplication. Okay. Another example. Let us assume you want to simulate 100 throws of a 6-sided dice and calculate the arithmetic mean of the outcome of these dice throws. Okay. So what we do is we define another word, colon throw dice, and this just expects a number on the stack, the number of throws you want to throw the dice, and pushes a 6 on the stack. Over copies the 100 below the 6, so we have 100, 6, 100, and performs reshape. Reshape is an incredibly powerful operation. This is the simplest example of reshape. Reshape takes a structure of arbitrary dimensionality and reshapes it into another structure. The simplest case is to reshape a scalar into a one-dimensional vector. This is what we do here. We have on the stack a 6, 100, and perform reshape, so we get a vector of 106 elements. The next step is to execute the question mark. As an APL, this is our pseudo-random generator. This will apply automatically to every single element of this vector consisting of 100 values of 6. So we get a vector of 100 pseudo-random values between 0 and 6 exclusively. We take the integer, add 1, so we have values ranging from 1 to 6, 100 of these in this array. Apply reduce to the operator plus in this vector. Swap the remaining 2 elements, so we have the sum of this vector containing pseudo-random elements and 100 divided, and what we get is just the mean of our simulated throwing of dice, 3.35. Okay, Fibonacci numbers. I really struggled to find a solution which is at least a bit as elegant as the one Larry showed 2 days ago. I have not succeeded now, but I will not quit thinking about this. This is a very straightforward recursive definition of Fibonacci numbers as you all know them. Every Fibonacci number except the first 2 is defined as the sum of its 2 predecessors, and this is exactly what this does. The interesting thing is the definition of this word, fib, and in curly brackets, a u. This defines a new unary operator. All other words you define without specifying curly brackets will just work like ordinary fourth words. If you define a word as a unary word, it will automatically be applied by the interpreter like every built-in unary operator to every element of arrays, except regardless of their dimensionality. So this word can be applied on a single scalar or on a 1 or 10-dimensional vector, whatever, it will be applied automatically to every element. So if I have this Fibonacci word, I can just write 10 iota, creating a vector 0 to 9, and then fib, which will be applied to every element, and will calculate fib 0, fib 1, fib 2, and so on. and dot will just print the result. And the result is, as expected, 1, 1, 2, 3, 5, 8, 13, and so on. This is where the real strength of 5 and 4 comes from, that you are able to extend the language within the language itself. As it turned out, many extensions we programmed over the last more than a year by now. Over the last year were really written in 5. That's what's behind this loading mathlib and loading standardlib.5. Okay, I have a horrible example, and I hope I don't frighten you away. This is Fortran, not suitable for children. This is a real example from a Fortran 2003 book. They really write code like this. And what they are doing is they want to compute all numbers between 1 and 999, which are equal to the sum of the cubes of their individual digits. As you can see, they need 3 loops. They will compute the numbers, 100 times h plus 10 times t plus u, and will look if these equal h to the power of 3 and so on. Really horrible, these explicit loops. When I got this book, I immediately thought this must be way easier using 5, and it is. That's the solution, 5. We define the word cubesum, curly brackets u, so it's a union word. I can apply it to a vector or array, and this does nothing very complicated. I push an empty string on top of my stack and apply a split. Split does exactly what split does in Perl. Of course, we take as many operators from Perl as we get. So if I have a number on the stack and I push an empty string on top of this number and apply split, what do I get? A vector of all digits of this number. Then I push a 3 on the stack, perform the power operator, star star, so I have the cubes of my individual digits. Then pushing the operator plus on the stack, applying reduce, I have the sum of the cubes. This accepts a single number and returns the sum of the cubes of its individual digits. The next line is the actual main program 999 iota yields a vector of 999 elements. 1 plus, I have a vector running from 1 to 999. Tuk tuk creates 2 copies of this vector. And on the last copy, I will apply the cubesum word. So the last vector will be replaced with a vector containing the cubesums of the individual elements of this vector. Then I issue an equal operator, which will yield another vector with 999 elements, 0 or 1, regarding where 1 denotes every place where the original vector has the same value as the vector containing the cubesum. The next step I do is I apply select expects a vector, and on top of this vector another vector containing of true and false values. And it will just copy the vectors which have a true value in the corresponding selection vector. So everything I get back are just these numbers which equal the sum of their cubes. 1, 1, 5, 3, and so on. And by the way, the Fortran book even made a mistake. They missed the 4 and 7. Okay. This is a little bit stranger, creating a list of primes. Still no explicit loops, and a horrible inefficient algorithm, but it's beautiful. The idea is the following. I don't want to divide by all odd numbers or something like this. So the idea was stolen from a book with APL examples, and the idea is great. Suppose you want to calculate all primes, generate a list of all primes between 2 and 100, for example. What you can do is you create a matrix consisting of all multiples of 2 vectors running from 2 to 100. What you get is some kind of a lines. What has lines of English? Okay.
101?
What 101 table?